3.3 Systems of Equations. So far, we've been working with equations, mainly a singular equation. Now we're going to talk about what happens whenever I have multiple equations, in particular, multiple linear equations. This is actually what we call a system of equations, or a system of linear equations. A system is a set of equations in which each equation is linear. It should be each equation, not which equation. For example, here I have a system defined by two linear equations. This big curly bracket indicates that this is part of a set. In particular, for whenever I talk about a system, we like to talk about a solution to the system of linear equations. This is a point, or points perhaps, such that each equation is true. Remember, for linear equations and pretty much every other equation, we can always check our answer to see if my solution is correct. Well, for a system of linear equations, I want to make sure that that solution I have works for every single equation I have chosen. So, now that we know what a system of linear equations is, another definition is, what does it mean to be consistent, independent, inconsistent, dependent? So, if I have a system of linear equations, we have one of three scenarios. First off, if there's only one solution to the equation, then my system is called consistent and the equations are independent of each other. If my system has infinitely many solutions, then we have a consistent system, but my equations are actually dependent of each other. And if the system has no solution, we just say that the system is inconsistent. So I either have one solution, infinitely many solutions, so like all real numbers, or there is no solution to my equation. So, what happens with these three scenarios? Remember, linear equations can be graphed as a line. So if I have two linear equations, I can graph two lines. So when I have one solution, the moment that both equations are true is where they intersect each other. So if I have one solution, this means that my lines intersect at one point, such as what I have in this first picture. They intersect at a single point. We have one solution. Whatever this x comma y point is, that's our solution. If I have infinitely many solutions, meaning my solution set is all real numbers, the only way for that to occur is if my two lines are actually the same line, like what I have in this second figure. The two lines completely overlap each other, so every solution works out. Or infinitely many solutions, to be more exact. And then my last situation is what happens whenever I have no solutions. Remember what I said earlier. My solutions are where my lines cross each other. Well, I know of an example where I have two lines that never cross each other. That's something that we call parallel lines. Parallel lines never cross. Hence, they have no solutions to the system of equations. And that's what we have here in the third picture. So these are the three figures that we're looking at. So how do I solve a system of equations? System of linear equations, to be exact. We're going to learn about two methods. One being substitution, and the second being elimination. So, to solve a system by substitution, for one of my equations, either the first one or the second one, I want to solve for a variable of my choice. Maybe you want to solve for y, maybe you want to solve for x. In whatever case, after I solve for one variable, I'm going to substitute that variable into my other equation. In other words, I should end up with a single equation. After I get that single equation, I solve my new equation. And then that will solve for one variable, If I have one variable, I can solve for the other. If that sounded a little bit odd, don't worry, we're going to go ahead and you're going to see a little bit nicer whenever we do an example. So, example 1. Here I have a system of linear equations. Solve the system. I have x plus y is equal to 9, and 3x plus 4y is equal to 30. So, if I want to do substitution, one thing I can do is, let's look at this first one, for example, the one on top. Actually, let me go ahead and label them as equation 1 and 2. From equation 1, I can actually solve for example, y. If I solve for y, I can get y is 9 minus x. This is still the same equation as equation 1. But now I have a single variable by itself. Substitution says I take this equation and then I'm going to plug it into my second equation. In this case, I plug in for y. If I do this, I end up with 3x plus 4 times 9 minus x is equal to 30. Again, I replaced that y with 9 minus x. Now, all I had to do is solve for x here. The first thing I would probably do to solve for x is let's get rid of our parentheses. And we can do that by multiplying my 4 to my 9 minus x. If I do that, I get 3x plus 4 times 9, I get 36. 4 times negative x, we get negative 4x. And this is equal to 30. So all I did was distribute the 4. Now I combine any like terms. Let's see, I got a 3x and a negative 4x. 3x minus 4x, I get negative 1x, or just negative x if you want to write that, plus 36 is equal to 30. From here, I could subtract 36 and get negative x is equal to negative 6. And remember, I want x. I don't want negative x. So let's divide by negative 1. Giving me x is positive 6. Let me rewrite that 6. So I have my x value. But remember, my solution is an ordered pair, my x comma y. I need to figure out what y is as well. Well, the reason why I said that, well, I didn't really say it earlier, the reason why this is going to be a lot nicer for us is, remember, in the way beginning, I said y is equal to 9 minus x. In other words, if I know what x is, I know what y is. So, using this combined with what I know about x, I know y is 9 minus 6, or simply 3. So I have my x and my y. The last thing I'll do is I want to express my answer as an ordered pair, x comma y with my parentheses. So I have my final answer. I'll double box it for us. So this means whenever I plug in 6 comma 3 into equation 1, then it's true. If I plug 6 comma 3 into my second equation, it's also true. And you can check this answer if you wanted to. You will see that it is in fact true. So we are done with example 1 through substitution. So for example 2, I'm actually going to go ahead and leave this to you as an exercise. Go ahead and pause the video. I'm going to go ahead and write the solutions for this equation, but I'm not going to work it out. See if you can get this final answer that's going to appear on the screen. Alright, so I've gone ahead and shown the solution for this equation. As it turns out, this equation has no solution. What I did here is I took equation 1, solved for y, and then I plugged that y back into my second equation. If I work all of this out, you should have eventually gotten to a very confusing result. You would have ended up with, well, 4 is equal to negative 5, which is a big what? That's not true. Since 4 is obviously not equal to 5, that means, first off, I couldn't solve for x or y. And secondly, this means that I have no solution. There is no way for me to solve for x or y. So this is example 2. Now we're familiar with substitution method. The second method we can talk about is the elimination method. And actually, instead of going through the instructions, you can read them, take a moment to pause and read them. Let's go ahead and just jump straight into example 3. Solve the following system. I could use substitution if I really wanted to, but let's use elimination for practice. Here I have 5x minus 8y is equal to negative 47, and negative 6x plus 2y is equal to 26. Once again, I'm just going to label these as equation 1 and 2, respectively. So what I'm going to do is I'm going to determine a variable that I want to eliminate. So if I compare equation 1 and equation 2, let's look at my y values, for example. I could have said x values, but it's going to turn out the y values can be a little bit easier for us. For the first equation, I have negative 8y. For the second equation, I have positive 2y. Well, what happens if I look at equation 2 and I multiply the left and right by 4? So I'm saying, what happens if I multiply the left and the right by 4? If I did that, equation 2 then becomes negative 24x plus 8y is equal to 26 times 4. That should give me what? 4 times 20 is 80. 80 plus 24, I get 104. So this is my second equation if I multiplied it by 4. And remember, I'm allowed to do this. My equation is still legitimate as long as I did the same thing on the left and the right. And now for convenience, I'm going to go ahead and just recopy my equation 1. So I did not change equation 1 at all. So this is going to give me the hint, why did I even multiply equation 2 by 4? Well, if I look at these two equations, what happens whenever I add the two together? Adding straight down along the line. If I do this, I get 5x minus 24x, giving me negative 19x. And then I have negative 8y plus 8y. Those will give me 0y. They form a 0 pair. So I'm left with negative 19x on the left, and on the right, 104 minus 47. 104 minus 47, I believe we should be getting 57. So I have negative 19x is equal to 57. Notice that my y's are now gone. They canceled each other out. So by multiplying equation 2 by 4 and then adding them together, I was able to get rid of one of my variables. Now I can just solve for x. I can do that by dividing by negative 19, giving me x is equal to 57 over 19, which I believe does not simplify down. Or does it? Oh, yes, it does. It simplifies down into negative 3. So I have my x value. Now that I have my x value, I can solve for y. So, to solve for y, I'm going to go back to my original two equations. Allow me to erase this times 4. So, I know whenever I plug negative 3 into the top or the bottom, I should get the same y value. So you can choose one of your choice. So just to mix it up a little bit, let's go ahead and plug x equal to -3 into equation 2. If I do that, I get -6 times -3 plus 2y is equal to 26. Now I can clean this up, giving me 18 plus 2y is equal to 26. To continue to solve for y, I would subtract 18, giving me 2y is equal to 8. And then dividing by 2, giving me y is equal to 4. So, for my final answer, I have the ordered pair, parentheses, -3, 4. I claim that this is my final answer. So this means that whenever I plug -3, 4 into my two original equations, then they should be both correct. So you can go ahead and verify that for yourself by just plugging them in quite nicely, actually. So the method I just used here was called substitution. I meant elimination. Elimination is that we quite literally are trying to eliminate one of our variables by adding or subtracting our equations together. So let's go ahead and look at example 4. Example 4, same instructions, solve the following system. This time I got 2x minus y is equal to -12, and then -2x plus y is equal to 12. So we'll actually be able to solve this pretty quickly. Notice I have 2x and -2x. I can actually just go ahead and add these right from the start. If I add these two equations together, I get 2x minus 2x giving me 0, -y plus y giving me 0, -12 plus 12, I get 0. So 0 is definitely equal to 0. And that's always true. What does that mean? Well, for this to happen, this actually means that I have the same line. Notice that here on my second equation, if I multiply the whole thing by -1, I simply have 2x minus y is equal to -12. That's exactly what we had up here. Well, if I actually have the same line, then there's not much I can really do in terms of solving for x and y. As it turns out, all I have to do is write infinitely many solutions, because we have an unlimited number of ordered pairs that would work in here. We're not specifying which ones, but we know that there exist infinitely many. So this is what we did for example 4.